Thanks, Roger. I will talk about message authentication today, and this is joint work with Gorian Alagic, Alexander Russell, and Fang Song. So I assume not everybody in here is familiar with with some of classical cryptography. So I will start by introducing message authentication. So in this scenario, Alice wants to send a message to Bob, and I think Bob is hiding behind this gray box. This is a typo, I guess. And she wants to send her message to Bob, but how does she send it? Of course, she sends it via the internet, and all kinds of stuff happens on the internet. So how can Bob tell that this message actually came from Alice, and that it is actually unchanged? So the solution to this problem in classical cryptography is the so-called message authentication code. Okay, thank you. I can't hold 3 items at a time. I will just. I think it's fine without a pointer. So the solution in classical cryptography for this problem is a so-called message authentication code. So that's some efficient function MAC, and this is used in the following way. So now Alice and Bob start out with sharing a secret key K, and Alice now sends an encoded message in the following way. So she calculates the value of the function MAC with input M and K, which is T, a so-called tag, and then she sends the message and the tag through the internet. And in the end, it might be changed or might not be changed, but Bob can now do the following. He can just take whatever he has received and recalculate the function MAC and check whether this is consistent with the tag he has received. So that's basically what Bob does. He just checks consistency with the function MAC. Of course, this doesn't work for all functions. So the function MAC has to fulfill some properties, and now let's have a look what kind of properties this is. Of course, what we are worried about is somebody forging a message tag pair. So this could be some adversary here that just goes about and comes up with a message tag pair without any help, or it could be an adversary that intercepts a message tag pair and forges another one. So just uses this information to create another a different message tag pair, or in the most general attack model, we have this adversary here that can make an arbitrary number of queries to this oracle that is the MAC function for a fixed key, and use this information to create a message tag pair that is not equal to any one of the ones he queried to the oracle. Okay, so basically the key property of this MAC-K function is unpredictability, right? So no matter how many input-output pairs of MAC-K the adversary has observed, he cannot predict how this function behaves on the input he has not queried. Now let's get a bit more formal. So formally, we have this game where this adversary sends queries to a MAC oracle. A first one gets a tag back, and then maybe adaptively chooses a second message and gets a tag back, and does this maybe Q times, and in the end outputs a pair M star T star, which is supposed to be a message tag pair. And the success of this adversary is, of course, defined by M star being not equal to any of the queried messages, and this pair being consistent with the function MAC-K. So this basically, and a MAC is called secure if no such adversary exists. And this security notion is called existential unforgeability under chosen message attacks, or EUFCMA for short. Now, what this talk is basically about is the quantum setting, in the sense that we are still talking about a classical cryptographic scheme, a classical MAC, but we assume that an adversary has gained quantum oracle access to it. So what happens in this scenario? So let's look at a little example here. So okay, now I will actually use this thing. Let's assume that an adversary just prepares this uniform superposition state here. So he takes a uniform superposition of all messages and queries this quantum oracle for MAC K once to obtain this uniform superposition of message tag pairs. Now what he can do is just measure in the computational basis, and he ends up with a random message and the corresponding tag here. And now the adversary outputs this pair. So this is, of course, something that we should not be worried about somehow, because in a certain sense, he didn't create like a new message tag pair. This actually came from the query, right? But in some sense, EUF-CMA definitely doesn't make sense anymore, because how can we compare this forgery, this candidate forgery, with the query? The query has been a quantum state, and it was a superposition of exponentially many messages. Also, it doesn't exist anymore, so we literally can't compare the two to determine whether the forgery is fresh or not. So bottom line is that EUF-CMA doesn't make sense anymore in this setting. So then basically now we're back to square one. We have to come up with a new way of measuring success of this forging adversary. So yeah, in particular, what makes an algorithm a good predictor of a function if it has quantum oracle access to it? So the example that we just saw, essentially this is not a good predictor. We kind of know that. But then let's have a look at an example of a good predictor. So here we have a random periodic function fk, and we define the MAC by setting it to 0 at the period, at the input that is equal to the period, and equal to fk everywhere else. So now there is a simple prediction algorithm, or a forger that runs period finding on this function here to find pk, and then just outputs pk, 0, because that's how we kind of designed this thing. And this, we know that this should be counted as a good predictor, because basically the algorithm barely queried this this pair, pk 0. In particular, we could remove this part of the input state of the adversary, and it would still succeed. So this should somehow be counted as a good predictor. Now let's have a look at a previous approach to this problem, and this is by Bonnet and Jandry from QCrypt 2013. So they just said, okay, fine, we cannot check whether a forgery is fresh. But if we just ask the adversary to output as many input-output pairs as they made queries, plus 1, then we know if they're all distinct, then at least one of them cannot be equal to any of the queried inputs. So in particular, more formally, we have this version of the game where the adversary makes Q queries again, but then they have to output Q plus 1 input-output pairs. And the success is again defined, or the success is here defined by all of the Q plus 1 pairs being correct. This has some nice properties. For example, if we restrict this game to, or this definition of a forger to a classical oracle, we get back EUF-CMA. So that's a nice sanity check. And also a random function is actually unpredictable, which is something we strictly expect to happen for any good such definition. But the question is it really right? Because somehow we are asking a lot from the adversary. We ask from them to basically not only use their queries to come up with a fresh forgery, but to also kind of keep a copy of their queried message tag pairs in some sense, right? They have to use each query very wisely to come up with this Q, with at least Q input-output pairs, and then forge an additional one. So in particular, what happens if an adversary, for example, has to make a couple of queries and then fully measure them in some basis to generate a forgery? So that way, basically, it seems like they maybe came up with a fresh one, but destroyed all their state to do this. So then maybe they cannot win this game, but in some sense they should be counted as successful forgers. Or maybe an adversary makes just one query and outputs exactly one input-output pair, but it queries in one place of the message space, and then outputs a message from a different part, right? Maybe the query is completely supported on this red region here, and the output, the forgery, is supported on this, or is from this gray region. So in some sense, it feels like we should be able to come up with a counterexample in the sense that it's obviously broken, but fulfills this definition here. But this turns out to be quite hard in some sense. And one reason is that for many problems one can come up with, if there exists a forging algorithm, then it can kind of rewind and then still succeed with a good probability. For example, with the period finding example. So now, after some thinking, one can come up with a counterexample that is basically obviously broken, but secure according to this BZ definition of unforgeability. And it works like this. So we have take two random functions, f0 and f1, and a random large subgroup of z2 to the n. And now, first of all, we randomize. We make f0 symmetric on this subgroup A. So basically, we make it constant on cosets of A. And on the other hand, f1 we modify in a way such that it is equal to 0 on the dual group of A. That's on all strings that are orthogonal to the elements of A. And it's equal to the random function elsewhere. And now we define a mag that's basically the two functions pasted next to each other. So it's a function of a bit and a bit string, and the bit chooses the function, and the bit string is the input to one of these two functions. Okay, so this is the mag, and there's a simple algorithm that this simple one query attack. Basically, we can use Fourier sampling on the first part, on the zeroth function, basically, to get a random element of the dual space, and then we just output the forgery using the second part. So this would be 1x here. Now we can forge on the second part because we have constructed in a way that the function is 0 on all elements of the dual space. But on the other hand, we can actually prove, and that takes a bit of work, that there's no algorithm that makes one query to this mag and outputs two distinct input-output pairs. And that's basically because we constructed in a way that it needs a sampling process. And that, in particular, that kind of destroys the state because we have to make a measurement with many different possible outcomes. Okay, so this basically shows that we're back to square one again and have to come up with a new definition of unforgeability against quantum attacks. And we came up with a new approach, and that's basically what if we can't compare the queries and the forgery, we can just basically make an artificial oracle that refuses to correctly answer on some inputs and then ask the adversary to forge on these particular inputs. So basically, we blind the oracle to give like dummy answers on a subset, and then we ask the predictor to predict the value on these on this blind set of inputs. So more formally, we select a subset of the input strings by independently putting each input into it with probability epsilon, and then we define this modified oracle here that that answers with this bottom symbol on all blinded inputs, and otherwise it answers correctly with the MAC value. And the corresponding definition then is, of course, reads like this. So a MAC K is blind unforgeable if for every adversary with a quantum oracle for the blinded function, the probability of the adversary outputting a correct input-output pair that where the input is in the blinding set is negligible. So now we want to check, does this make sense, the new, this new definition? So first of all, it's also equivalent to EUF-CMA if we restrict to the classical setting. So that, that's relieving. Also, a random function satisfied. So that's the other sanity check. That's very important. But then in addition, it actually classifies the examples we have seen of functions correctly according to broken or secure. And this is the very simple one where the adversary just queries the uniform superposition and then measures and outputs a random input-output pair. And there basically, the adversary outputs basically m comma bottom for if it turns up a blinded message, and otherwise it will output a message that's not blinded and then a correct tag. So it will never succeed. On the other hand, our counter example, here the adversary does Fourier sampling on the red part and then outputs a forgery on this olive part here. And here we can easily see that this is actually broken as well. So if the oracle is only blinded on a couple of random inputs, then the output change will not change too much, the output state. So basically, this Fourier sampling still works. But then the Fourier sample on the olive part is blinded with independent probability epsilon. So basically, the adversary will essentially succeed with probability epsilon minus a little bit. So this is successful. Okay, so this is my last slide. So a couple of additional results we have, which I cannot go into detail of. So we have a new security of hash functions that generalizes collision resistance and strengthens this collapsingness notion by Unruh. And with this, the hash and MAC approach to authenticity is secure under this new blind unforgeability security definition. Also, such a hash function can be constructed from LWE, and Lamport signatures are also one-time blind unforgeable. Let me skip the tools part because I think I'm running out of time. Basically, a couple of recent tools by Gendry, basically, and Bonnet. We have used, and then this is the outlook and the summary. So the question is, of course, did we solve the problem? And the answer is we don't quite know. Maybe we solved it. It seems like the new definition is quite apt at classifying everything we know correctly, but one kind of caveat is that it doesn't imply BZ. It doesn't imply the previous definition. And the question is, of course, does this matter? But at least this is something that gives us something to think about, for sure. And more generally, I think this is a good motivation to initiate a more fine-grained study of quantum query complexity. And that's all I have to say. Thank you.
Okay, thank you very much. Are there any questions?
A quick question is, you said something different than what's written there. You said it does not imply BZ, and you wrote it seems hard to show that it implies BZ. So which one?
I meant. Oh, sorry. That's true. I said something that's worse than reality. Yeah. It seems hard to prove that it implies BZ.
Yeah. My question was just which is correct, like what you said.
It is hard to prove, or we find it hard to prove. We don't know.
Okay.
Yeah. Sorry about that.
And regarding this other notion, like the Garg, Zandri, UN notion, does that?
So that's a one-time notion, right? So basically, the main difficulty only shows up when we go to multi-query, the multi-query situation, where because in the one-time one query setting, basically this kind of simulation-based approach works, where one can basically define an ideal channel from input to output, because there's like an input, then one encoding, then there's the forging algorithm, and then there's one decoding to check whether it's correct. So basically then we can like take this encoding, attack, decoding process and define like an ideal functionality for this map. So this approach fails if we have if we allow multiple adaptive queries, and that's why basically it was a bit simpler, this Garg, UN, and Jandri setting. Also, it's an extremely strong definition. It's stronger than the one-time variants of both of these.
Maybe just a broader question. So in terms of when you motivated this, so you said, okay, we have max, and you transmit max over the internet. And so the classical definition of security for max, the game that you gave us, this kind of makes sense in that setting, because you assume that the adversary just sees all these messages and tags sort of fly by in the internet, and you don't want it to be able to. But then, so what? Somehow. So this quantum notion is a bit more strange, right? Because you typically don't have access to assigning or superposition. So I was wondering if you have a motivation for it. That's one part of the question, and the other part of the question is if the kind of results that you're finding are not sort of broader than max, and maybe max are not the best setting in which to express these kinds of findings, in terms of you're asking questions of, how do I quantify that I created new information or something outside my queries?
So I want to say that definitely they are broader than, the results are broader than just max. For sure, they also apply to signatures, but then I think the underlying questions that I kind of brushed over, which are in this last 3 points here, are basically about the power of a single quantum query in some sense. Like the quantum query complexity as it is developed as a field doesn't ask these fine-grained questions about if an adversary has exactly Q queries, for example, and then has to output Q+1 input-output pairs. This is a question that's difficult to ask within the framework that exists, because there it's always about a polynomial number of queries for a fixed task. So somehow I think the results are interesting in a broader context for sure. And about the motivation part, maybe we should soon take this offline, but about the motivation part, so I think the motivation is both that there are different situations where quantum oracle access is actually very natural, and so it's interesting to study the setting inside of cryptography. And then the other thing is that if at some point we have a lot of quantum computing infrastructure, we don't want to be very careful about never implementing our classical Mac on the quantum computer.
Okay, I think we should finish there for this session. So there is now a break until 3:45, and just before that, let's thank all the speakers from this session again.